Hey everyone, Gene here. Today we're diving deep into Java multithreading, specifically exploring executors, futures and thread pools. This is the 6th video in my Java multithreading series, so if you're new here or missed the previous ones, be sure to check it out in the Java Advanced playlist. We're going to take a practical approach. We'll not only learn the theory, but also build a real-world example to calculate Euler's number using these concepts. This will give you a solid understanding of how to apply these techniques to your own projects. So just for a quick recap on what Euler's number is, it's a mathematical constant and it is denoted by the letter E. It looks like this, and the formula for it looks like this. Let's break down the key concepts. An executor is a powerful tool that decouples task submission from execution. It's like a task manager that handles the scheduling and execution of tasks. However, it has some limitations, such as not being able to return results or easily cancel tasks. Executor service is an enhanced version of Executor, addressing its limitations. It provides methods to submit tasks, track their progress, and retrieve results. You can also schedule tasks to execute at specific times or intervals. A future represents the result of an asynchronous computation. You can use it to check if a task is complete, cancel it, or retrieve its result. Thread pools are a collection of reusable threads that can be used to execute tasks. They help optimize resource usage by avoiding the overhead of creating new threads for each task. Now let's put these concepts into action. We'll write a Java program to calculate Euler's number using multiple threads. This will demonstrate how to use executor service, callable, and future to efficiently perform parallel calculations. Alright, let's create ourselves a code example in Java. Let's start by defining ourselves an executor pool. So this is like a basket of available pools that we allow the application to use, and we can limit it to a certain maximum number of threads that can be used. So let's define a new variable for that, final static int pool, which we set to 2. Meaning that we allow 2 threads at a time, and let's also print out the settings. For that we make use of the printf method, and we output pool and the number that we set. Alright, now let's define the actual process. For that we're going to define a new callable, which returns a value of type big decimal. So why do we make use of big decimal instead of just using float or double? Well, big decimal is just a bigger number, so we just have more possibilities. The number of positions after the decimal point is limited to int. So in other words, the quantity of numbers that we can display ranges up until about 2 billion, which is a bit bigger than float or double. Alright, let's call it callable and create a new instance. And inside we override the call method, which is the method that will be executed. It's very similar to the run method, but with the difference that it returns a value. In this example, it's big decimal. Okay, let's define the precision that we want to calculate with. For this, we're going to make use of the math context class, and let's also define a new variable for that, final static int precision, which we set to 100, which means 100 numbers after the decimal point. Alright, let's also create an output for that by making use of the printf method, which outputs precision and then the number that we defined, which is 100. Now let's provide the precision number to the math context. We also need to define the rounding mode, which we set to half up. Now we define ourselves another big decimal variable, which we call result, and which we initialize with 0. Now we can start calculating Euler's number. You might have asked yourself, why would we calculate Euler's number? And that's true, because we could calculate just about anything, because we actually just need an algorithm that keeps the thread busy for a certain while. And Euler's number is very good for that. Alright, now we define ourselves a for loop, which will handle the number of terms that we want to add to the result. So the more terms that we add to the result will end up giving us a more precise Euler's number at the end. Let's create a new variable for that, final static int terms, and set it to 4000. Let's also create an output in the print settings for that, which outputs terms and then the number that we set. Now let's make use of the terms variable in the for loop, so that we define that the for loop runs from 0 until to the number of terms, and the iteration is a step of 1. Alright, for calculating Euler's number, we first need the factorial. So what is the factorial and how is it calculated? The factorial of a non-negative integer n, denoted as n exclamation mark, is the product of all positive integers less or equal than n. So in other words, if we want to calculate the factorial of 3, it's 1 times 2 times 3. So 1 times 2 is 2, and 2 times 3 is 6. Let's build a method for that. Private returns big decimal factorial and takes a big decimal in. In here we define ourselves a new variable result of type big decimal, which we set to 1. And then we define ourselves a new for loop where we start with a big decimal I of value 2. And then the for loop runs until I equals n, which we can do by using the compare to method, which will equal 0 if I and n are equal. And in every iteration we add 1 to the big decimal. And every iteration we multiply the result that we already have times I. And after that we return the result, which is the factorial. Now let's calculate the inverse, which is 1 divided by the factorial that we just calculated. So big decimal 1 divided by factorial. And then we add this to the result variable. After having done all the terms, we return the result at the precision that we defined in the precision variable. Alright, that's all we want to do in a callable. Now let's define ourselves a new variable, tasks, which is a list of futures of big decimal placed into an array list. In here we will put all the threads that we create. For that, let's also create a new variable to define the number of threads, final static int threads, which we set to 10. Let's also create an output for that using printf, threads, and then the number of threads. Now let's go back down and create a new for loop, which runs from 1 until to the number of threads. And in every iteration, we create ourselves a new future, returning a big decimal. And then we take the executor and make use of the submit method, in which we place the callable. And the result is a future that we can handle later. Let's not forget to add this task to the task list. And that's about it for this loop. Now we also need to tell the executor to shut down. Otherwise it will never end. Alright, now we want to check all the threads if the tasks are done. And as long as they are not terminated, we continue to check. In every iteration we print the stats, meaning we print the shutdown, which we get from executor is shutdown, terminated, which we get from executor is terminated. But we also want the pending threads, which the executor service in this form does not have. So let's go up and change the class. Let's deactivate the executor service that we defined and make use of the thread pool executor, in which we place executor's new fixed thread pool and place an implicit convert to thread pool executor. Alright, let's go down again and enjoy more possibilities. Now we can access the queue and the size. We can also get the number of active threads by executing the getActive count. And we can also get the number of completed tasks by making use of the getCompletedTaskCount. Now let's create an output for that by using the printf method. Pending, active, shutdown, and terminated. Let's also limit the speed that we check and pause in every iteration for 1000 milliseconds. Alright, that's about it. Now there's one thing that could be interesting. Let's also output one Euler's number, just to see what we calculated. For that we create ourselves a new variable Euler's number of type big decimal, in which we place task, get 0, and get. Now let's print this to the terminal using printf, first thread result, and then Euler's number. Alright, that's it. Now let's execute the application. And here we can see the printout of the settings that we have, which is precision 100, terms 4000, a pool of 2, and 10 threads at a time. Now the duration for this depends on the single core performance of your CPU. So you will always have 2 threads working at the same time until all 10 threads are done. Once they are done, pending will be 0, active will be 0, completed will be 10, shutdown will be true, and terminated will be true. And the last line will be the first thread result of Euler's number, which is 2.718, and so on. By understanding executors, futures, and thread pools, you can write more efficient and responsive Java applications. Remember, practice is key, so experiment with these concepts and build your own projects. But we're not stopping here. In the next video, we'll delve into advanced synchronization primitives like countdown latches, cyclic barriers, exchanges, semaphores, and phasers. These tools will help you build complex, concurrent applications with ease. So if you want to master Java multithreading and take your programming skills to the next level, make sure to subscribe to this channel and hit that notification bell. Also, make sure to hit the like button of this video. Thank you very much for watching, and I'll see you in the next video.